It would be the first falsification, if you like, of general relativity. To me, that sounds mind-blowing. This is possibly the biggest outstanding problem in physics at present.
What if everything we thought we knew about testing quantum gravity was wrong? For almost an entire century, physicists believed that probing gravity's quantum nature would require some massive particle accelerator the size of our solar system. But Professor Chiara Marletto and Professor Vlatko Vedral of Oxford have both discovered something revolutionary.
We identified the sweet spot.
Theories that are mainly classical, such as Penrose's collapse model, would be refuted.
A way to test quantum gravity using pretty much today's technology. Their groundbreaking proposal, known as gravitationally induced entanglement, could become the first experiment to prove that gravity itself has quantum properties, falsifying Einstein's classical theory of general relativity. I'm Kurt Jaimungal, and on this channel, I explore unification in physics and philosophy using my background in mathematical physics from the University of Toronto. Today, it's a special treat with staggering implications from Oxford's Chiara Marletto, who I spoke to before on constructor theory, link is in the description, and Vlatko Vedral. If successful, this would mark the first experimental evidence that gravity must be described by quantum mechanics, radically redefining our understanding of the force that not only shapes our universe, but in some sense is the backbone of our universe. Chiara Marletto, Vlatko Vedral, thank you so much for coming onto the podcast. Welcome.
Thank you for having us.
Pleasure.
To set this up, many people know in the public, even in the physics community, they at least believe that quantum gravity is something that, sure, we can theorize about it, but testing it remains something that you can do 100 years in the future, a century from now. You need a collider the size of the solar system, people say. Those are technically called high-energy signatures. So you just put out, both of you, a paper 3 weeks ago or so, outlining something called the GIE. What are these experiments that test quantum gravity, and why would they disprove classical theories like Oppenheim's or Penrose's potentially? Why is this important?
Yeah, it's a great point actually that for most of this research into quantum gravity, and maybe I should say that this is possibly the biggest outstanding problem in physics at present, how to unify quantum mechanics and general relativity. I think for most of this research, people thought that you indeed needed high energy. The hypothetical particles that mediate gravity, the gravitons, the analogs of photons, are really so weak that it's difficult to see how to detect them in any lab-based setting that we are aware of. In fact, so much so that you had people like Freeman Dyson writing papers that even though it seems problematic, unifying quantum mechanics and general relativity, it doesn't matter because the two will never be seen together in any meaningful context. And actually, that's what surprised Chiara and myself, that we found a setting where I think this could work. And it's in low energy. It can be done in the lab, and that's something that we're exploring at present.
Yeah, and I think the interesting fact about this test is that it uses some information theoretic ideas to work, and so the gist of the idea is that if you can use gravity as a channel to create some kind of particular correlations between two masses, so you can get the masses entangled following a specific protocol, then this fact that gravity can function as a channel that can mediate entanglement is like a witness of the fact that gravity has some quantum features. So it's a very general idea. It doesn't really tell you which particular model of gravity would work for quantum gravity, but it tells you at least that if gravity can do this, so if it can mediate entanglement, then it certainly does have some quantum features. So as you said, theories that are mainly classical, such as Penrose's collapse models, or even Oppenheim kind of model for for classical gravity, would be refuted. And it's a very surprising thing that this, as Vlatko said, works at low energies. But somehow the price to pay is that you can't confirm a specific quantum gravity model, but it's like just a witness of the fact that gravity has some non-classical features to it.
Yes, I think it rules out a host of what you would call semi-classical descriptions. So descriptions where everything other than gravity is fully quantized, and of course we know how to do that, and then it's sitting in some kind of classical space-time, classical curved, if you like, a general relativistic background. And it seems to us, at least, that these theories can be shown to be inconsistent already with a very simple low energy level experiment, and they could all be ruled out. And that definitely surprised us, because it certainly does not involve any detection of gravitons, anything like that. And as Chiara said, you could then take this as not being able to discriminate, possibly because between all the genuine versions of quantum gravity. That's the downside, maybe, of that.
Yes, but the plus side is easier. It's closer to feasible experiments that you can do nowadays. So I think this is really within reach in some sense, with, of course, some considerable experimental effort.
Yes,
but it's much closer than other proposals that had been suggested before.
It would be useful at this point to distinguish between the two concepts that sound similar to the layman, which is unifying general relativity and quantum mechanics, and quantum gravity. So what makes a unification attempt between GR and quantum mechanics quantum gravity versus just reconciling them? Chiara.
Yeah, I think that's a good question. So the quantum theory of gravity is there are in fact lots of proposals for different quantum theories of gravity, but what they all have in common is the fact that they take seriously the idea that gravity is capable of if you like, of processing quantum information. So unlike general relativity, which is fully classical from this point of view. So if you consider Einstein's theory of gravity, it's as classical as Newtonian gravity. So in that sense, it was a leap forward compared to Newtonian gravity. But in terms of the information theoretic structure, it's still much the same in terms of, so it can only instantiate, if you like, bits, classical bits. Whereas all quantum theories of gravity are implementing this idea that the gravitational field, or gravity more broadly, can exist in superpositions of different states, and it can also mediate things like entanglement and other chiefly quantum phenomena. Whereas if you just want to reconcile quantum theory and theories of gravity, you can do this in a number of ways. And not all of them will require gravity to have quantum features. In fact, there are many proposals, some of which we mentioned earlier, where people try to imagine a world where there are quantum particles that have mass and energy, and therefore they interact with gravity, but then gravity is still described completely classically, or at most with some stochastic element in it. So a bit like classical randomness. So it would behave a bit like a classical coin that has like randomness in it, but it's not associated with the existence of quantum effects. So I think this is the difference between the quantum theory of gravity program and let's reconcile these two theories, gravity, classical gravity, and quantum theory. And somehow the difference between these two approaches is that while in the case of quantum theories of gravity, you're thinking that quantum theory is actually universal, so you're trying to really extend the quantum theory to gravity itself. In the other approach, where you're trying to simply reconcile them, you're imagining a world where quantum effects stop applying at a certain scale, and specifically they stop applying when there is an interaction with gravity. So there must be some mechanism through which the quantum features of, say, a mass that, for example, is in a quantum superposition, get destroyed or dampened by the fact that it interacts with gravity itself. If you are in this other approach where you're thinking of a semi-classical theory of gravity or even a classical theory of gravity that is in interaction with the quantum world. So yeah, I think these are the two differences.
I think it's very interesting because this concept, it really is related to the concept of the field, which is probably the most important concept in modern physics. When Einstein was asked, do you stand on the shoulders of Newton? And he said, no, I stand on the shoulders of Maxwell. And the reason being that Maxwell actually mathematically, Faraday invented the concept, but Maxwell formalized the concept of the field and, of course, phrased the electromagnetic field in this way. And so the question for gravity, if gravity mediates between objects that we know are otherwise quantum mechanical, and then it seems logical for consistency reason that it ought to be able to behave quantum mechanically. Because if it has to communicate between objects that are themselves in a superposition of being in many different places at the same time, then gravity needs to somehow originate from each of these places simultaneously, which is exactly how the electromagnetic field behaves. So I think that's kind of what occurred to Chiara and me, that in fact, it should be relatively easy, at least conceptually, to test this by simply forcing gravity to act on superpositions. And all it takes for our proposal is, in fact, two massive particles, each in a superposition of two different places. And now the question is, if the gravity really remains classical, that's almost what Roger Penrose would probably say. If gravity remains classical, then it ought to choose one of these interactions, because now there are four possibilities how they could interact with one another. Each of the two places of one mass could couple to each of the two places of the other mass. So Chiara and I are betting on the fact that this happens simultaneously, which is where the resulting entanglement comes from. Whereas a semi-classical person would probably say, no, gravity ought to choose one of them, collapse, and get rid of the other three possibilities. So I think that's kind of, very crudely speaking, what's at stake.
So superposition of space-time itself, of the geometry itself, is what distinguishes a semi-classical or classical theory of gravity being combined with quantum mechanics versus a quantum theory of gravity?
That's an interesting subtlety, actually, that Chiara and I like to discuss, and we did it in the paper that you mentioned, but over to you.
I think there is a difference between preparing gravity itself in a superposition of different configurations. So if you think of a field, you can think of different configurations of the field or a superposition of geometries or whatnot. And the fact that gravity is quantum. So you can have some features of quantumness. So for example, the ability to create entanglement is one feature. And the ability to be set into a state, which is a superposition of classical configurations, is yet another feature. And this test that we are discussing checks the former, so the fact that you can use this gravity as a channel to create entanglement, but it doesn't really prepare gravity in a quantum state that has the property of being in a superposition of different configurations. So it's more showing that gravity must be described by an object that isn't classical, which in jargon we call a Q number. So something that has the property that when you consider it together with the classical features of gravity, such as some of the properties that you associate with gravity that are classical, if you consider these two things together, then they can be measured simultaneously by the same instrument, by the same measuring device. But this other Q number that mediates the entanglement, which is the non-classical aspect of gravity, doesn't necessarily have the property of being preparable in a quantum state. This is an extra property. So the experiment doesn't show that you can put gravity into a superposition, but it shows that it has a minimal set of properties that make it different from a classical object. And so it cannot be described by a classical field or by a classical set of numbers, which are all commuting with themselves in a way and therefore measurable at all by the same instrument. And I think this is a subtle difference.
It is a subtle difference.
Which is important to
Indeed. And I think maybe to put it this way as well, to add to what Chiara said, that this is a necessary property to talk about superpositions. If you didn't have this, then clearly you wouldn't even have superpositions of different spacetimes. But to create the superposition of spacetimes, you may need to do more. And then there is a question of whether this is really feasible to do or not. So it's interesting that our experiment, if successful, wouldn't necessarily tell you whether you could superpose these things. You would have to do another experiment to really try to prepare a superposition. The reason why I'm thinking is that it could simply be that these superpositions decohere. They're simply coupling so quickly to everything else in the universe, because the gravity basically has that feature that it sees everything, if you like, that in fact you cannot maintain the superposition for too long. And these are what you would call super selection rules in physics, that there are quantities that, even though they are quantum fundamentally, in this first sense that Chiara was describing, you still cannot utilize it fully. You're not allowed to make some superpositions because they would get you into trouble with other things. So it's a very interesting thing. But I think certainly the thing to check, to test for beyond this proposal.
Yeah, so just to make it also a bit more clear, so I guess that the test for superposition, if you want to check that something is in a superposition, you need to do an interference experiment directly on this entity. So for example, a photon, you can set it up in a way that performs an interference experiment with some device, a Mach-Zehnder interferometer or some kind of interferometry, so that you show that it has some wave-like properties, if you like. With gravity here, we are testing lesser property, so that the photon has as well, which is this ability to create entanglement, to mediate quantum features between two other quantum objects. But it's not the full set of quantum properties. Really, if you really want to check that something has this property of being in a superposition, you need to set up an interference experiment on the object itself, so in this case with gravity. But I think that's the thing that's very hard to do, and that's what it's actually practically impossible to do, because the quantum particles of gravity, the gravitons,
that's right. I mean, if
are not detectable individually.
Exactly. If you trust Freeman-Dyson's conclusion, I think you would say that the corresponding experiment with the graviton would never be done, actually.
While with the photon is relatively accessible because it's been done many times.
Yes.
With gravity, this experiment, the interference experiment with gravitons, can't be done. And that's because of the difference in fundamental constants and the way they couple and all of that. So I think that's somehow how this experiment, this test that we proposed, somehow manages to bypass this problem by testing a different property, which still shows that gravity is quantum, but in a different way. It's an interesting fact.
Okay, I think the audience has been teased enough. So we'll get to the experiments in just a moment, the GIE experiments. First, I want you to spell out specifically what's meant when you both have been using this word mediate. Gravity mediates entanglement, or supposedly, or potentially. So that's something I'd like you to spell out. I'd also like you, when you start to talk about GIE, to distinguish it from Bose's initial experiments or proposals for experiments. Yes. And maybe in your paper, you've outlined Page and Gelker and Cal. If you think those will take us off track, then you don't need to go into Page and Gelker or Cal. But if you think that that's useful as a stepping stone, then feel free to.
No, we can do that.
It's good. It's good, actually.
Good. Yeah.
Floor is yours.
So shall I just... I can say a few things about this mediation generically. And actually, then you can even decide whether this fits in or not in the long story. I think these are all very beautiful topics.
I think about the mediation,
So physics is, like I said, all about fields, and actually, what's behind that is locality. So we believe that all interactions in physics take place at the same point. When two entities interact, they must be in the same point at the same time, and then they could affect the neighbors, and then the neighbors affect the neighbors, and then this propagates. So this was a main problem for Newton, by the way. His gravity was action at a distance, and he himself was extremely troubled by this. There are exchanges, letters with other scientists at that time, philosophers, where he acknowledges that no one in their right mind would think that planets can affect instantaneously one another. So the genius idea of Faraday, which, by the way, Maxwell formalized, and then Einstein took on board from the electrodynamics and applied to gravity, basically to introduce a field in between so that a planet only disturbs its neighborhood, creates gravity in the neighborhood. That gravity propagates like a wave at the speed of light, and then it affects other objects. When it reaches another object, it shakes the other objects locally. And that's basically your mediation. That's what we call a mediator. The field mediates the force, if you like, between these entities. Now, this was very important because you couldn't have conservation principles if you didn't have fields. That's what's interesting here. Let me give you a very simple example. When a planet it's close to the sun, it moves faster. It has a higher kinetic energy. When it's further away, it has lower kinetic energy. Now imagine it's very close to the sun and it starts to move away, which means it loses energy. Where does the energy go now? And now you say, well, it takes 8 minutes for that signal to come from the Earth to the sun. But that doesn't sound logical to a physicist that for 8 minutes energy is not conserved. It goes God knows where, and then suddenly after 8 minutes, sun picks up the momentum and says, oh, the Earth just lost some energy 8 minutes ago, I better speed up a bit. That would be very funny if it operated like that. With the field, there is absolutely no problem. The energy is stored in the local field, propagates to the sun, then the sun picks up that, and overall the field, together with the two objects, perfectly conserves energy, momentum, angular momentum, anything else. So that's the true value for this concept of the field. Now imagine quantum mechanically, and I think that's part of what Chiara and I, what our argument relies on fundamentally. In quantum mechanics, objects can be in two places at the same time. So now, in order to conserve anything, the field better understand how to respond simultaneously to the object in place 1 and the object in place 2. So a classical field doesn't understand what that means. That's why, as Chiara was emphasizing, you really need these Q numbers to also describe the field, because the field must be able to respond simultaneously and conserve all of these entities in both places at the same time. And actually, that's key to our experiment. That propagates locally to the other particle. And in this picture, all of these principles are beautifully upheld. So I think a problem for any of these semi-classical theories is even bigger. They literally don't know how to strictly conserve these entities. They maybe have to do it stochastically on average, things like that, probabilistic conservation, but they can never do it exactly. And somehow to us, this looks like a huge price to pay. That's why it sounds kind of illogical that gravity is not quantum. But I think you wanted to...
Yeah, no, I wanted to just comment on the fact that I think more broadly speaking, the mediation requires there to be, so if you have two entities that, like in the experiment, that interact with each other, there's one way that can, as you were saying, it can happen that they interact directly, so they just talk to each other directly, or they don't talk to each other directly, but they talk through a third element, to a third system. Now, this third system could be a field with all of the mathematical apparatus that describes a field, but it could also be a more general entity, so it doesn't have to be a field necessarily. But as you were saying, it's important to have the idea of the interaction happening not instantaneously directly between these two objects if they are space-like separated, so they are distant from each other in a sense. But there has to be a third system, which in this case is gravity, that mediates the interaction.
Indeed. Yeah.
And so in a way, this test that we are proposing does assume that the interaction is mediated in this way. And I think it's a good assumption because, as Vlatko was saying, this is what
it parallels the rest of the rest
most
of physics.
theories of gravity that we've had that are meaningful, not just Einstein's general relativity, but other proposals as well, are mediated in this way. And this is a difference from Newton's gravitation theory, because in that case, Newton himself had the issues with the fact that there was this instantaneous action at a distance, which bothered him a lot. And that's because the interaction was not mediated.
Indeed. So actually, and this is a nice point also to link back to what we said. This is yet another set of theories that we couldn't rule out. So we can't rule out we can rule out semi-classical descriptions, but out of the quantum descriptions, even the weird descriptions like non-local signals back from the future and things like that, none of that would be actually invalidated by our experiment.
Yeah. You mean all the classical descriptions that are not mediated.
That's it.
Are not tested by our experiment. So they could still maybe be able to create entanglement, but they would do so in a non-local way.
Yes.
And we think that there are lots of strong reasons to just assume in the background knowledge the fact that we have the locality is satisfied and that we have a mediated interaction for gravity. But that's an important assumption. So it was nice that you asked the question.
Yes.
Maybe
the difference with Sugato Bose is another interesting point to make there.
Yeah, I think Sugato and
so we published. We published these papers together in Physical Review Letters, and by complete chance, because we spoke at the same conference. And we realized that we had very similar ideas. So then we suggested to actually wait to have the manuscripts ready together,
and we publish them independently somehow, but jointly in the same issue, right? So that it would appear at the same time.
Which is nice that it worked out also with Physical Review. And
I think Sugato and his collaborators were very interested in a specific experimental proposal. So they had a different rationale from what we were thinking. The experimental proposal uses specific particles so it's the same test that we're suggesting, but somehow they are specifying a particular setup with nano crystals that are, so it's kind of set up in a particular technology, if you like. So there is a particular setup to implement the idea. So they spend, there's a nice section with details about this. So I would say it's more applied, if you like. Whereas
maybe also to emphasize, this fact that the proof there, I mean, this is a sort of a technicality, but an important one, that what they did to mimic classical behavior was in a way not to allow any entanglement in this mediator. So in a way, the argument is maybe not as general as what Chiara and I had.
To say that we were more interested in the abstract theoretical side of things, in the sense of trying to find a more general argument to support the experiment, as you said. And so I think while Sugato is using a theorem from quantum information theory, which is called the local operation and classical communication theorem, that says basically that you can't create entanglement with local operation and classical communication. We generalized that theorem because we felt that it could not be applied directly to gravity, given that gravity may not obey quantum theory. So this is a kind of subtle point, but somehow you can't apply quantum information results to something that, like gravity, may not obey quantum theory itself. So we wanted to be more general.
We wanted to be as agnostic as possible.
As convincing as possible to a skeptic who might think that gravity is not quantum, because ultimately this test is for those people in a way. We kind of all maybe believe that gravity is quantum after all. So we wanted to have the fewest assumptions. And so we didn't want to assume the quantum theory is described by, the gravity is described by quantum theory. And for that, we developed an argument which is broader and has only general axioms. So it's based on this constructor theory of information. That's something that
it's beautiful because it goes back to Chiara's PhD. And actually, the techniques are very nice that you are really talking. I mean, this is again making it very. It's a crude statement that I will make, but somehow you're really showing the incompatibility between systems that have different capacities for information processing. So it really says you cannot get the full range of information dynamics between two quantum systems if whatever helps them in this, any mediator, doesn't have the same capacity to process information. So you can phrase this in a very, very general way through information theory, through constructors.
Yes, and how we arrived to that was that we started with Vlatko, we started discussing around about the time of my PhD, I think.
We argued a lot, I think.
We had a discussion about, on the one hand, how useful the constructor theory of information could be. So I was looking for something like an application of it. And at the same time, we had this nice paper that, I think I started discussing with David Deutsch by DeWitt. So DeWitt had this argument, Bryce DeWitt, who was one of the founders of quantum gravity, if you like. He had a paper where he wanted to show that what you just said, that it's impossible to have a quantum object that interacts with a classical object unless you give up something. And in his case, he assumed a number of axioms to prove this, which were very specific. So to Hamiltonian dynamics, so he had a lot of assumptions. And then when we started discussing this argument with Vlatko, I think Vlatko quite rightly was dissatisfied with this. And then I thought, okay, maybe constructor theory can help with this because we can relax the assumptions that DeWitt had and try to reproduce his argument in the constructor theory framework.
Yes.
And then from that, we ended up thinking, hey, actually, this is interesting because it sounds like we actually can test non-classicality of an object by creating entanglement between two quantum probes. And that's how we ended up then we checked that this was feasible.
That's right.
And that's how the paper came about. So
it's interesting that we had a sequence of prior papers that I think, unless you're really into this field, you wouldn't see a natural progression. But we tried a bit with a single probe, and then we could never get a watertight argument that whatever drives a single probe it can be conclusively also then proved to be quantum.
Yeah, a single mass, right? So
a single mass, let's say. And then it occurred to us, indeed, what you said, that by using two masses and thinking of the mediator as a channel between them, this is possible.
Yes, and I think so this kind of ties back into the with the question about Cow, the Colella-Overhauser and Verne experiment. I think the Cow experiment is with a single quantum mass. So it has a neutron that is in a quantum superposition of different locations, and it's been performed. And I think it's actually the realization of an idea that Feynman had back in the 50s when he was at this conference, the Chapel Hill conference, where there was a lot of discussion about quantum gravity, and Feynman was trying to convince Hermann Bondi that quantum theory of gravity would really make a difference as opposed to a classical theory of gravity where there is some randomness infused into the gravitational dynamics. And Feynman said, well, look, I mean, ultimately, you would have to show that you can superpose a mass and then the gravitational field joins into the quantum superposition, and then you can do some interference experiment with this. And so that was the first time that I would say someone formalized, maybe in a memorable way, this idea of having an interference experiment where gravity participates. But it was with a single mass. And this was then effectively implemented with the Cow experiment with neutrons. But there, the problem is that you can describe this with a quantum theory of gravity, but you can also describe this with a classical theory of gravity. So a classical theory of gravity would be, without extra assumptions, you can describe this neutron interferometry that the Cow experiment represents. You can describe it with a classical theory.
Yes, because it only affects the phase locally.
That's right.
And you can describe the classical.
So the interferometry on the neutron can be explained perfectly well with a background field that is classical.
Yes.
Whereas in our case, because we have two masses, each of which is in a superposition, so that's the extra added bit that both Sugato, Steam, and us had. So the idea is really to use two interferometers with two masses, two quantum probes, and then use gravity not just as a way to create phases on each of these two interferometers, but also to create correlations between two of them that are quantum. So chiefly entanglement, but maybe also other forms of quantum correlations would work. I think there are some works by Paterek and collaborators where people are thinking of different forms of quantum correlations that would still work as a witness. And I think that's somehow the difference between our proposal, Sugato's proposal, and the cow experiment, and actually all of the other experiments of the kind that Feynman thought originally. And then Page and Gailker. Page and Gailker is like an intermediary milestone, I would say, where I think
even less conclusive than the cow.
Yes, and I think they themselves say this. It's an actual experiment. But it's designed really to rule out a specific kind of semi-classical theory of gravity, where the idea is that if there is a quantum mass and it's superposed across different locations, then the field somehow must be in an average of the two configurations that each of these two locations would create separately. And I think the experiment is designed to rule out this specific theory of semi-classical gravity, which is somehow very narrow, I would say. It's not. Yes. So I think they wouldn't say that this proves the fact that gravity is quantum. Not at all. But it's a way to show that some of these semi-classical models are really somehow very narrowly applicable, and they don't make sense in most cases where there is a quantum superposition of a massive object. So they can be used in certain approximations. They are useful for computing things like, I think the Hawking radiation is computed with that assumption and other things. So they're okay in some regimes, but I think they are very narrowly applicable. And this has been known for a while, I would say.
Yes, I think if you force a classical account, then you have to somehow stochastically add these two contributions from, let's say, if your mass is in two places, then somehow you have to decide how much of each of these places contributes to your ultimate field. In quantum mechanics, of course, you do both. You have an amplitude for one, amplitude for the other, and the usual is to add up amplitudes to calculate the final interference. So I think that's really what's at stake here.
But the experiment had nothing quantum in it. That's
nothing
what I wanted to say. That really was not set up at all. There's no quantum coherence.
There's no interference.
At all, yeah, that's right.
All right. So to summarize, you looked at DeWitt's arguments about gravity, the quantum interaction, and you weren't satisfied. So you used constructor theory, which is generally extremely abstract. Even some people are like, well, what's the use of constructor theory? You used that to prove something more general called the general witness theorem, even though that name wasn't given so far. I believe that's okay. And in the discussion and development...
People call it by various names. That's why, sorry. There are so many names now in the literature, I think.
Yeah.
Yes.
I see.
That's a nice name. I think it makes sense,
Now, in the discussion and the development of this theorem, you also, both of you, have developed the idea for this experiment called the GIE. So please now outline the GIE.
Yeah, so GIE stands... Yeah, thanks. Yes. The GIE stands for gravitational induced entanglement. So it's kind of quantum correlation induced by gravity. And that's what you want to test in the experiment. And the way you generate this effect is to set two quantum probes, each in a quantum superposition of, in the specific case, different locations. So there are two masses, two quantum masses that can be prepared in a quantum, each in a quantum superposition of different locations. And then you let them interact gravitationally with each other. Because they are in these quantum superpositions, each of the branches of the superposition acquires a different phase. And this sometimes leads to the fact that the two masses are entangled. And if you're skillful enough in the experiment so that the experiment can guarantee that it's only gravity creating this entanglement, and you can also test the entanglement, then you can conclude using this general witness theorem that gravity that mediated the entanglement is indeed non-classical. It has these features that are quantum. The general witness theorem is very general, so it can be applied to a number of different settings, but the specific setting that I described is for gravity. And you can also use different quantum probes. It doesn't have to be masses in different locations. It could be a superposition of different energies, so long as these different branches of the superposition can interact gravitationally. I think that's the important
I think that that's the
aspect.
challenge, that, as we know, gravity is by far the weakest force. So we need an object that's massive or energetic, as you say, enough that during the time that you can keep this superposition. So the challenge is always, how long can I maintain an object in a superposition of two places at the same time? Because of various noises and decoherences, this cannot usually be done for a long period of time. So we need to choose something large, but larger objects usually decohere faster. So these are kind of the trade-offs that we have to take into account. But I think Chiara and I thought, even in that first paper, that we identified the sweet spot, that there are the right numbers at that time that actually would give us maximum entanglement. Not just any entanglement, but in fact could generate a maximally entangled state.
Yeah, I think these estimates were very rough in a sense, but they were also very encouraging. So this was something that also Sugato and his team found out, that you can do this with masses that are about a nanogram. So whether 10 to minus 12 kilograms or 10 to minus 14 kilograms, that kind of range, which is much larger than obviously something like the mass of a neutron. Or even
an atom.
Yes. But it's quite close to what the current technology can do. And importantly, this is the thing that surprised the quantum gravity community to some degree. It's several orders of magnitude lower than Planck's mass, which is this mass that is 10 to minus 8 kilograms. That's supposed to be the relevant mass for seeing quantum effects in gravity. So this somehow was supposed to be the threshold for being able to actually elicit any quantum response from gravity, the Planck's mass. But turns out with this experiment that you can actually do it with a consistently lower mass. So that was a promising thing. Of course, there are feasibility studies that have to be made about the actual experiment. But let's say with the back of the envelope calculation type thinking, this is what we estimated, which was why we got very encouraged by the results.
Yes.
Yeah.
Okay, so going back to locality, you implied that entanglement is a non-local effect, but it's always created locally. So let's say we have an electron and it's interacting with another electron right here, and then they become entangled. They separate. The talking that was referred to earlier is because they have some quantum numbers, spin up, spin down, and they need to tell each other something like, it may not be the realist case where it says, I'm going to be up, you're going to be down, I'm going to go off this way, you go off that way, but they somehow need to talk to each other.
Yes.
Then there's a mediator. Yes. So just like how when you're fighting with a friend or a spouse, at some point you need a mediator, maybe you don't want to talk directly, you talk to someone else and say, you talk to that person for me. You're wondering, okay, is it the case that if instead of these electrons speaking to one another, can they speak to the geometry or to gravity, and then that gravity speaks to the other electron, or photons in this case? Is that broadly correct? And then the witness theorem says, how are you able to tell if that happened?
That's exactly it. Yeah. It's brilliant. It's brilliant. Actually, your analogy is fantastic. Imagine that that you are not sure whether you want to divorce from your wife or not. And you tell the mediator simultaneously, yes, I would like to proceed with the divorce, and no, I wouldn't like to divorce. I'd like to stay married. So now, unless the mediator is capable of simultaneously communicating communicating to your other party these two messages. So the mediator would, in a coherent way, the mediator would now have to walk over to your partner, go to their house, and somehow simultaneously communicate the fact that you would like to divorce and not divorce at the same time. And that would be exactly...
Yeah, and the only way to do that is if the mediator itself can be in a
can be quantum. Otherwise, if you talk to a classical mediator, they would choose one of the two options, and then you would never be able to pursue both at the same time.
That's right. So I think that's a nice analogy. Yeah, it makes sense.
Right.
That's what, and the witness theorem allows you to, under some assumptions, to say that this is the case indeed. Yes. That if you can successfully perform this mediation through gravity, then gravity must be non-classical in some aspect. Yeah, and I think that's the power of the argument, but also its limitation in a way, because it doesn't tell you exactly what theory of gravity, what theory of quantum gravity should be used to describe what's going on in the experiment. So that's up for,
Yes. In fact, our experiment could be modeled by what people call the lowest approximation to general relativity. So even if you take the first order expansion, you just do that quantumly, you would fully account for what Chiara and I are predicting. And then, of course, a natural question, if we're discussing open questions beyond this, it would be, what about the next order? How do you know? Because gravity is nonlinear. Gravity, in general, if you have strong gravity, you would have to compute higher orders. Then, of course, our experiment doesn't say anything about that. And in fact, they are much weaker than the first order contributions. So that's one thing Chiara and I are thinking about, is how would we test higher orders? How would we know if the whole of GR is quantum, not just at this level of approximation?
Well, wouldn't testing, I assume you're referring to linearized gravity? Or
That's
no?
It.
Linearized GR?
Yes, linear
yes.
GR.
So wouldn't testing that already be a huge breakthrough? Like, you're thinking 10 steps ahead, and it's already Nobel Prize winning. If you were to... Are you then saying the graviton is what mediates? Or are you just saying the geometry? Like, what is it that's the mediator between the two photons?
The beautiful thing is that this still stays an open question. You could pursue both of these. You could say it's consistent to think of gravity just as a field sitting on some kind of background space-time, which is how Feynman would have quantized gravity, or De Witt or Weinberg. I think all of them are field theorists in that direction. Or you could go like some other approaches, like loop quantum gravity, and say, no, you ought to quantize space-time. The geometry itself must be quantum. Areas, volumes must be quantum objects. They don't commute, if you like. They're Q numbers. And our experiment doesn't suggest which of these two approaches one should follow. Both, in fact, would be consistent with the entanglement. So that's also very interesting to explore. What does this tell us about the nature of gravity? Is gravity really different to other fields? Should we quantize space and time directly? And our experiment doesn't resolve that.
No, it doesn't resolve that. Yeah, that's right.
Now let's paint out what this experiment is concretely. I mean, paint the picture. Do you take a laser in a beam and then you split it and then you measure so-and-so? Like, tell us exactly what an example of this experiment would look like.
It's a beautiful question, actually, and I think it really helps. It really helps imagine what's going on. As Chiara said, there are many ways of doing this, but I think there is one way that's possibly clearer and easier than others. It's the one that we are investigating now, and I think a variant of it is what Sugato had in mind as well.
Yes.
Do you want to?
Yeah, I think Sugato identified in this proposal he had a specific technology, which is to use microcrystals that have a spin degree of freedom that's attached to them, which can be used as a sort of label, as a handle to guide them into creating a massive superposition. So these are crystals that have a mass, which is of the kind that we need, and plus they have a spin, and the spin is used as a handle on which you can act with a magnetic field to set up a massive spatial superposition.
So maybe even, do you want to start even at the beginning of the story, how the experiment would go with this lattice of crystals. Then you shoot a laser to kick one
Yeah,
out.
so
Then you
somehow these microcrystals can be grown into a substrate, which is something that quantum materials people would be able to provide, and then they you can actually address individually each of these microcrystals in the
lattice.
in the lattice, and then you would like to knock out two of them to then being able to use them in this experiment. And now the question is, how do you set up the device that creates the superposition once they are knocked out of this array of solid state array that they are generated from? So I think Sugato had an idea with a system where they would be dropped. There would be like a free fall. There was the initial proposal that he put forward in this theoretical paper that he had. And some of his collaborators kind of followed up on that, investigating that setup. We have some collaborators in the National Institute of Metrology in Torino, Marco Genovese and his team, who are looking into a slightly different setup which seems easier to realize, where in fact you are going to trap these two nanocrystals into a magnetic trap, where they are trapped in 2 dimensions, and 1 dimension is the one that allows them to move around and create a superposition. And so once they are trapped into this trap, which is basically made with an electromagnetic field, you use a magnetic field that's of sufficient strength to manipulate each of the 2 microcrystals individually, and you move them around to create the superposition. And then, while they're still trapped, you let them interact with gravity only.
So this splitting, just to add for those that are familiar with this, would be like a Stern-Gerlach type experiment. So if the crystal is spin up, magnetic field drags it one way.
And
if it's spin down, it drags it another way. And because it's simultaneously up and down, it goes both ways at the same time. So that's how you make a superposition. And to interfere them at the end, you would need to do the reversal of this. You would need to reconfigure the fields in the opposite direction.
Yeah, so this is like closing a Stern-Gerlach interferometer with these much more massive entities, which are these microcrystals. And that's the challenge, because no one has done this before with such massive objects. In fact, even closing the Stern-Gerlach interferometer was only very recent, and it was done by a team with Ron Follman and Sugato.
Who are also interested in this.
I think so. So I think but this was done with masses that are much lower than the masses needed for this experiment. So I think, so the setup is really like that. And to read out the entanglement, you need to measure these objects at the end of the interferometer in appropriate ways and check the correlations between these 2 massive objects, and that confirms entanglement if there is entanglement. So
one should say that an advantage is that you can keep these crystals in a superposition over a very long period of time. So various other groups have demonstrated, we're talking seconds or more. Which is required roughly for our test. And they used a lot in quantum information for all sorts of purposes to detect very sensitive fields in the vicinity, vibrations. So we know that they're suitable for this kind of metrology, which is the good news. There is a lot of know-how in the community. But as Chiara said, doing even a single Stern-Gerlach, just half of what we want, I think is already a groundbreaking experiment. Nature probably front cover, that kind of thing.
Yes, and you could test also lots of things already with one interferometer. There are lots of interesting foundational questions that you can test with that.
Certainly repeat COW almost as a warm-up experiment to put a static classical mass in the vicinity and see whether this superposition can detect it. That's, I think, one of the milestones we could probably achieve.
Okay, so let me see if I got this correct. The setup is you obtain microcrystals. These microcrystals have something called spin degrees of freedom. You then have to knock out 2 microcrystals from a lattice using a laser.
Yeah.
Yes.
You then use a magnetic field to trap these microcrystals into a spatial superposition, something like a Stern-Gerlach-like setup.
That's it, exactly.
And then you allow the microcrystals to interact gravitationally. I don't know how you allow it. Like, how could you even disallow them to
Allow means
interact?
that they would naturally. I think what Chiara means is that you disallow. Maybe that's a better way of putting it. Any other
I see.
interaction.
Okay.
For instance, we don't want them to couple electromagnetically. Spins
Yeah.
shouldn't couple directly.
So they have to be at a certain distance so that the other forces are not a problem. Then they have to be very low temperature. So it is a low temperature in the vacuum. So that you have to set up the conditions so that other things don't interfere with the effect. That's very challenging experimentally.
That's one approach. We're exploring
But there are a number
many.
of others,
There are a
maybe.
number of others. You can allow them to couple in all sorts of ways, providing you understand the
what-
contribution
that's
of these others. Then you can incorporate it. I
Yes.
think even that's possible.
Okay. So to summarize, you grow microcrystals in some substrate. I don't exactly know what microcrystals are, but it doesn't matter. You grow something. You then
these
use
are called-
lasers.
There are broad
One of
classes,
these broad.
but there are some of these
Diamonds, for
diamonds
instance.
made of carbon. So these are arrays of carbon in the form of diamonds. So
They are like a lattice of carbon atoms where one of the carbon atoms is missing, and that's what creates effectively a single spin, so to speak. It's not quite like that,
Uh-huh.
but almost like that. And you can then make any state of this, manipulate this spin, put it up, down, superposition, and that's exactly the one that achieves then your interference, if you like, the splitting.
yeah, the challenge is that you're not doing it in bulk in the array, in the solid state array, but you're doing it once they're knocked out, which is the extra difficult. I mean, it's a very challenging technological part to realize. But I think these techniques are known. There is a lot of know-how to manipulate these microcrystals, at least in the array.
And I should add that a few years ago, there was this big deal about closing all the loopholes in Bell's inequalities. And the Dutch group, Hansen, I think, was the PI on that project, did exactly violation of Bell's inequalities with these two nanocrystals. They separated them, I think, 1.5 kilometers or something like that in two different laboratories. And then they entangled them by sending light, by sending photons to each of these. So that maybe is a useful picture. That's kind of what Chiara and I want to do, but of course the mediation shouldn't be now electromagnetic, it should be gravitational. And then subsequently, when they entangled them at a distance, they violated Bell's inequalities. And because they were far apart, you could show that no signal can go between the two. So in a sense, that's why we are relatively confident that this is the right technology, given that so much of this quantum information has already been done there.
Okay. So what are the next steps? Tell me about the feasibility of this project.
I think the key thing, what we are doing now are the feasibility studies, really to show exactly the regime. And so what we want to do now is to really contribute to setting up this experiment. So I think it's crucial to be able to, once you're convinced through these preliminary feasibilities that this can really be done, then I think we ought to really proceed to do this. So on the experimental side, I think there is a lot of work to do, and most of this work is on the experimental side. What Chiara and I are doing as theoreticians, of course, is always looking ahead as well. So we are discussing all of these other things that we could be testing either along the way or something that comes even beyond this. So strengthening the arguments, testing other features, I think. But the key, I would say, for us is the experiment, to really now put as much effort into this as possible.
Yes, indeed. And I think unlike the theoretical studies, which are relatively inexpensive, the experiment requires funds. So I think that's what we are currently trying to find to support the experimental effort to implement the experiment. And it would be nice to have a number of these different platforms investigated, not just this one that I described. But it would be nice that different groups tried different ways to implement this, because it's a bit like the first times that someone proposed a quantum computing algorithm. They can be implemented in a different number of ways with different technologies. And I think there's no reason why a different way couldn't be easier than the one we're investigating right now. So I think in a way it would be really nice if there were concerted efforts with different groups around the world trying to implement this idea. And on the theory side, I think the one aspect that you mentioned, I think is interesting there are two directions that are really interesting to us, which is one is to try to model the dynamical, what really happens with gravity in different quantum gravity theories. That's an interesting question to model how they create entanglement. This might also touch on some inconsistencies that we currently have in quantum field theory and the fact that maybe that's not a good description for this. So I think the experiment could actually be a way to open a door to further experiments that might find ways to probe some holes in the current, understanding of quantum field theory applied to gravity. And the other aspect is to find ways of applying this general logic of constructor theory of information also to these other experiments with a single mass. So that's an interesting direction because there would be, with a single mass, it would be a temporal variant of the spatial experiment. That's the one that's based on the GIE. But there could be a version of the theorem that applies to a single mass evolving in time. And the mediator of this evolution, which would be gravity, could then be witnessed to be quantum under some assumptions. And the question is how to formulate these assumptions in a general way that's general enough and convincing, at least to the same degree as what we did for the spatial version. So that's another direction that's very interesting.
Yeah, somehow the idea is always to rule out as many things as possible. That's, again, almost quoting Einstein, right? The best theory is the one that's most prohibitive. So somehow you want something that rules out as many alternatives as possible in one go.
Yes, and I think it would be nice because anyway, in the ramp, in the building up to the final experiment with two masses, you will have to go through the stage where you only have one interferometer.
Yes.
And so it's nice that actually only one interferometer, you can actually test lots of things already. And it would be nice to have this general argument applied to a single mass.
Yes.
This is something we're working on with Giuseppe Di Pietro, who's a student here in Oxford, a DPhil student. So I think these are very exciting directions for us that we would like to pursue. But yeah, mainly the experimental effort is something that really needs long-term fundings to some degree because it's something that can't be done in 1 year or 2 years. It requires a stretch of perhaps 5
to 10 years, probably.
Perhaps 10 years.
Yes.
The budget is not huge in the sense that compared to experiments that you find in places like CERN, this is a fraction, like a minimal fraction of the budget. It's something like 5-10 million.
Yeah, I think this is the usual lab-based atomic
it's
molecular
a low-budget
physics.
experiment
Yes.
from the looking from the experimental physics side of things, but still requires some support that's continued over a period of time. And these days, this is difficult to find, I think. So,
yeah, the difficulty being simply that you are really open about this being a fundamental question. And I think usually funding agencies are really keen to pursue applications and you would have to then answer, what's the point of this? How can you apply it to the... And it's clear why quantum technologies, for instance, have been extremely successful. Precisely because I think people promise all sorts of things in, drug development. And even if these things are hyped up or really far away from the present, I think somehow there is a huge potential payoff. Whereas I think what Chiara and I are saying is this experiment would be phenomenal for physics, certainly, and for science in general, because it would be a first piece of evidence that Einstein's classical general relativity is not correct. It would be the first falsification, if you like, of general relativity. To me, that sounds mind-blowing. After a century.
Of confirmations of theories.
So to me, it sounds like people should really be, as you said, investigating all sorts of ways of testing this. It sounds like possibly one of the more exciting questions in science at present, but it is difficult to convince funding agencies of this.
Yeah, so this is such a revolutionary experiment if done and then confirmed. Many people listening would think, well, look at the budget of CERN. It's a few billion. I thought that fundamental physics was quite well funded. And it sounds like what you're saying is fundamental physics is underfunded, and maybe CERN has just taken all the funding. I don't know why. You could talk about why. As a segue to talking about why, how about you tell me your thoughts, both of you, on the Nobel Prize and how it went to AI this year for something that should have been physics. And sure, they had some justification. In fact, The Economist had an article called AI Wins Big at the Nobels. I'll put that on screen and in the description, as well as the link to your experiment and where people can reach out to you if they want to help fund it. So please tell me your thoughts on AI at the Nobel Prize this year and what that says about physics.
Yeah, I was very disappointed. I must admit, actually, that Chiara and I discussed it quite a lot. There is a trivial, I also read around various comments, there is a trivial sense in which people frequently say everything is physics. And I think, physicists probably above all other scientists do believe that physics should underpin other sciences, and that with enough understanding and possibly computational power, you will bridge the gap with chemistry that quantum physics really explains. All of chemistry ultimately goes into biology and so on. And of course, the people who developed methods in neuroscience, in medicine, in even economics, Nobel Prize winning economists are frequently physicists in microeconomics. However, I wouldn't quite call that contribution to physics. It is a contribution that's enabled partly by methodology that physicists use, and of course mathematics is key in this case. But I think that Nobel Prize really missed the point somehow. It went to people who are just very loosely connected with physics, I would say. So from that, in that sense, I don't think it should have been a physics. Maybe they could have created a separate category to give it to computer science or even neuroscience. In fact, they could have gone into medicine. But I don't think it belonged in physics. It would, of course, be very different. Now I'm going to take a huge leap. It would be very different if you could get an AI to come up with a new theory of physics. That it's in itself would be a huge thing. I personally have a very low opinion of AI, by the way.
You don't get emailed every day someone's new theory from ChatGPT?
That's it. Yeah. I guess they can simulate lots of things, and I know that they can probably fool various examiners. That certain things are written by students, by humans, and so on. So all of that is impressive at some level, but one must understand the domain and the limitations of this. I think our cat is more intelligent than any AI, by the way. People say a 2-year-old, but I would go even lower than 2-year-old is a super genius for AI. So in that sense, I think even that misses the point. I don't think they even discovered the physical basis of consciousness. I think that would be a huge deal. And possibly you could argue that deserves a Nobel Prize in physics, I think, if you understood human intelligence, consciousness in a physical way. But I think this is very, very far from this, and possibly sends wrong signals as well. Now it suddenly maybe encourages, it's already an area that's super hyped up. They don't need more glamour than that, I think. It just sends bad signals to young people as well, somehow.
Chiara?
Yeah, I think I broadly agree with that. More generally, I'm in a sense, I'm in the business of physics because of the glittering stuff that's to do with ideas, and that's in the Platonic realm, if you like. So stuff that isn't imperfect and subject to human errors and so on. So I understand that the dynamics of giving a prize in physics is often complicated and has lots of factors that are not necessarily to do with the actual ideas that are being awarded with the prize. So I don't have a high, in general, I don't look at these prizes very highly in a sense, and certainly it's not the reason why I'm in physics. But I agree that they are important and they send a message, especially maybe even to young scientists, and telling them what matters to some degree. So in my view, it's the question of understanding consciousness is very interesting. So that's certainly a good, it's a good enterprise to fund and to be interested in. But I don't think that the current way that AI is studied is going to cast light on that. So I think these are two different problems. And I'm sure that there are lots of mathematical tools that are interesting that you can find out by optimizing problems to make AIs faster or better at various tasks. But I don't think that digging that way will lead us to understanding how the mind works. So I think it would be nice, if you could, set up a prize or whatever, an award that could actually indicate that this is the right thing to do, looking into the foundations of the fundamental issues behind consciousness, which were interesting to people like Alan Turing. I think von Neumann and Turing, they have these seminal papers about what is a mind. But then somehow the approach that they followed then was lost, and we ended up looking at more like at optimization problems for certain specific tasks, which are a different kind of problem. So in a sense, I was also a bit disappointed by the prize.
Indeed, the people you just mentioned could have themselves been given Physics Nobel Prize. We're talking Shannon. We're talking
Shannon
about many
as
people
well, of course. Yeah, they were. Yeah, that's right. So in a way, I see this progress in the AI direction as very different from understanding what the mind does and creativity and so on. So I think we will understand it at some point. It's certainly within reach of science and physics. I do believe it's part of physics. I also think it's a problem for physicists to think about, not just neuroscientists and not just computer scientists. I think it's a concerted effort, a bit like with quantum information or information theory, that's within physics as well. But I don't think the AI direction is the right one at present. And going back to your other question about the, why is it that fundamental science is only known in the public as being fundamental physics is often confused with things like fundamental particle physics or stuff like that, which is investigated in places like CERN. I think it's just a question of fashions, and somehow the fashion grew in a direction that made this the case. I mean, it's just created this idea that this is what a theoretical physicist does, right? To look into more and more ways of improving our understanding of the standard model and things like that, and devising better and better experiments, maybe on the experimental side, to test more and more particles, etc. But the issue is that there are actually, and this is maybe something that is not as known, and perhaps podcasts like yours could are useful in this sense, because they show that there are other problems. There are lots of problems in the fundamental part of physics that are unsolved. Cosmology is a huge issue. We have no idea. I think cosmological theories are out there, but it's difficult to test them, and they have difficulties theoretically as well. The foundations of quantum field theory, which is the basis of the standard model, are also problematic. So I think quantum field theory were invented by people thinking that it would be like a shortcut to understanding something and maybe being able to calculate various things, but they didn't think of it as a theory that would last for centuries. They didn't think of it as a complete theory. No. And we're still using that to calculate things, and we forgot about all the problems that are at the foundations of the theory, and we're not looking into it.
Maybe at that time was difficult also, to be fair, to test certain things. Indeed, but now we are really reaching. That's what's exciting.
I think that's a very nice, interesting direction to look into, in my view. So trying to find something better than quantum field theory.
Yes.
And obviously quantum gravity. That's the thing we've discussed so far. As well as integrating these microscopic theories that we have with these higher level theories like thermodynamics and maybe the physics of life and the physics of the mind, which of course we don't have at the moment.
Yes.
Thermodynamics is very well developed, whereas the physics of life is not developed as much, and the physics of the mind is even less developed, I would say. But these are three broad directions that are full of interesting problems. And unfortunately, this is something that's not that known, especially even in the, for a young person who starts studying physics, these problems are not as visible.
No.
And I think we need to do something. I think it's our fault. It's the physics community's fault that we're not talking about it as enough.
I think largely it is our fault that, yes, I think I was I gave a talk at the Royal Institution the other day, and not during the lecture, but after the lecture, someone approached me to ask me about quantum computers. And I said to him, what excites physicists the most is actually being able to understand complex physical systems with this kind of computer. And I think he was shocked. He thought, oh, but that's no one talks about that. The public is not aware of the fact that actually physicists would love to use this tool back to contribute to physics, which is exactly what we're all about, really. But so that goes back to, I think, admitting that the fault is frequently with the community, that I think we don't spell these things out as much as we need to, probably.
Yes, and even with quantum computing, just to talk about fashions, what comes out often is the idea of having a new gadget, which is a universal quantum computer that can do all sorts of things, which is very cool. But the big deal about quantum computing, quantum computation, the theory of quantum computation, which started as a theoretical idea, part of it started here in Oxford with people like David and others. You were there as well in the early days as well, in some sense, with many others. So you were looking into things that were not interesting because they would produce a gadget, but they were interesting because they were useful to understand quantum theory. I think David was asking question about quantum theory itself.
Yes.
How does what does it mean for a qubit to be in a superposition? What is it? What does that mean? And then in your case, what does it mean that it gets entangled with another qubit? How can we quantify that? These are all mathematical and physical questions that are very, very fundamental. Whether or not that would lead to a computer, it's interesting, it's useful, but it's not what powered any of these people. Even Feynman, when he was thinking about quantum computers, wasn't thinking about the computational power really. I think this is what it should be. We've lost the passion, I think, for in the public, for the beauty of looking for theoretical ideas that are fundamental.
Although maybe the passion is there, it's just that we are not supplying it. Somehow that's my feeling.
The public doesn't know about these things, I would say. I think they know about quantum computing as a technological development, but they don't know about the beauty of the theory ideas that powered it. Even of the experimental ideas that powered it, which I think they were awarded the Nobel Prize.
On a couple of occasions,
that's right.
in
so
fact.
For experiments that were in the foundations of quantum physics and of quantum information. But again, they were not looking for a particular application. They were just enjoying, the idea of understanding how entanglement works, for example. And those are things that we need to cultivate, not just at the level of universities, but I think it's something that even schools should power, should just tell students, very young students about, because that's what makes physics interesting, really. And now, podcasts like yours are also useful for that reason, I think, because they can get young people to think about this stuff early on.
So before we end with your advice for young people, there are a couple of routes I can take this. So one is that AI Nobel Prize, is that signaling that the Nobel Committee believes there's a stagnation in physics? Is it signaling that they're not interested in fundamental physics, or as interested as they used to be, at least not this year? Is it worrisome because it opens the door for a generalization of physics? So now maybe the Fields Medal doesn't just go to string theorists. The Nobel Prize can go to a string theorist because they invented some math that was then used, even though it wasn't direct application.
Yes.
Like what is most troubling? And then while I have this in my mind, I don't know if it's the case that the public isn't interested in fundamental physics. Sorry, I have a biased set because I interact with a science-educated public or a science-interested public. But I find that not the physicists that I speak to on the podcast, but some of them off air seem less interested in fundamental physics, as if they've been disillusioned that we can no longer make progress in it.
And that's also true.
So it seems like the public is interested in it and the physicists aren't.
Yes, you're right. And that's funny. Yes. I think
that's
I
a
can
really nice
resonate
point.
with
I
lots
think
of
that
these
makes all
things.
sense.
Yes.
Yeah, I think this comment is true. And I think what I meant earlier was to say that the public isn't aware of enough interesting problems that are open in the foundational part of physics, in the fundamental part of physics. And that's I think, because of what you said, that the physicists are at fault in this sense, because either they got sidetracked by a number of administrative and sociological aspects of physics itself, the way in which physics gets funded and all of that, and then they end up investigating problems that are not so interesting, but they have the good thing that they are incremental and therefore they are more likely to be funded, etc., etc. Or it could be that generally there are some parts of the physics community that believe that they will run out of steam. That's possible too. But a combination of these two aspects has made it into what you said, that it's often the case that there are perhaps fewer people, the density of people who are looking for fundamental problems is kind of going down. And that's a shame, because especially in the early days of someone's career, instead of focusing on desperately trying to publish results that are perhaps short-sighted and not very interesting, but they get you into having papers in your CV and therefore getting a job, you should try to be you should be left free to think about something in peace. For a stretch of time that's sufficient for you to solve a problem. And this is something that young researchers don't have at the moment in physics.
Yeah, this is a larger cultural trend. Like I usually don't think about these things because I'm obsessed with questions in physics. I love physics too much to think about the bigger social aspects. But when I listen to John Cleese, the Monty Python John Cleese, talk about creativity and how the current industry has completely destroyed it, it's almost like I'm listening to a physicist talk about this. So this is across the board, I think, the state of affairs. It's not just science. We are simply not giving people enough space and enough freedom to do whatever they think it's exciting. And that's, I think, what got us all of these revolutions in physics in the past, as far as I understand history. But I think Chiara is right that the incentives somehow have been set up in the wrong direction these days to encourage this. Just go for it, for the hell of it. Spend 5 years thinking about some crazy idea. Even if you don't get anywhere, I think behavior like this should be encouraged on the fund. I understand if you work for industry, you can't afford to behave like this. But in science, exactly. But in science, I think this is the only way to do things. So it seems to me it's partly stagnating because of that. I think there is an objective side in terms of technology that we touched on before, that I think for a long time we really were not able to test some of these things. And then, of course, you can't blame anyone for that. If the technology wasn't there, if it took 50 years to get to that level, then I think that's partly the problem. And that's why we're excited to actually be in this state now, that we think that you can really go back and readdress some of these fundamental questions.
So where is it that people can find out more about you both for this experiment if they're interested in either getting it funded or helping getting it funded? Is there a website? Is there a URL?
Maybe
we have a number of websites that describe partly our own research.
So there are two individual sites of both of us, but then maybe to
personal websites.
Indeed, but to send the institute.
And then there is a website that describes our institute effort, where we also describe this particular effort for funding this experiment specifically.
Why don't you tell us about the New Frontiers Hub, which is the name for the Institute for Fundamental Physics that you both are setting up, correct?
It's like a hub that we set up a number of years ago here in Oxford, in Wolfson College, which is the college where we both work. And it's partnered with a number of other entities as well within Oxford, with physics, the Maths Institute as well, but also other partners around the world. And the idea is really to have a hub where we solve some of these fundamental questions that are open. One of them is this one that we just talked about. Another direction is the direction I have in constructor theory, and many others directions. I mean, you have directions in quantum biology and the macroscopic quantum physics.
Yes, quantum going into the macroscopic domain. Yeah.
And it's funded by a number of foundations. We have the Templeton Foundation, the John Templeton Foundation, the Gordon Betty Moore Foundation, and the Utopia Foundation, and a number of other governmental sources as well.
Yeah, so the US-based foundations are really the most likely source, and I think I'm extremely grateful to them, actually.
Yeah,
both of us, for they really made possible many of these things.
Pieces of research that would not otherwise have happened.
Yes.
Yeah. So I think in that sense, it's very nice that we have access to these private foundations, because they are more interested in open problems of this kind rather than kind of more applied things that are most likely funded by the governmental agencies. And that's I think we can just link to.
Yeah, they can either get in touch with us individually or through the site. Any of this is extremely welcoming.
Yeah.
What's one key takeaway that you would like the general audience member who's watching to walk away with? General audience member, number one. The researchers who are watching, number two. And the new students who are entering the field of physics.
Okay, the general audience, I would say this fact that we have, for the first time after many, many years, in fact, I would say over a century, a way to test whether quantum theory applies to gravity in an experiment that's within reach, which means in the next 10 years span, we can get to that experiment. So it's not something very, very far in the future, but it's something doable.
Yes, hugely exciting.
Especially if we focus on it. So perhaps this one takeaway. For the researchers, okay, from my side, I think this unexpected thing that I see time and again, that if you study lots of theoretical abstract ideas, in my case was constructor theory, there are very, very direct ways of applying these things to experiments. Obviously, at the theoretical level, they are still at the level of thought experiments, the way that we phrase it. But I think there are some of these abstract ideas that can be linked directly to experiments. And the whole field of quantum information was of that kind as well, that you had highly theoretical, relevant, deep ideas that are deeply theoretical, which have a very direct implication for experiments and applications. That's an unexpected but very possible and real thing that we should look for more into some ideas. So in a sense, you shouldn't forget about abstract ideas just because you're interested in applications.
No.
They often go hand in hand. And for the students, for a young researcher or a student, I would, recommend against probably all the fashionable things. Just forget fashions and follow what you're interested in. If you're in the business of science, you should just follow your heart, what you like. Because if it's to do something that you don't like, you can go to a different field and then earn money for a different purpose. But if it's really you're in science, you may as well just kind of focus on what you like rather than trying to fit into something fashionable, just to look like you're part of something. I think it's important to follow your own interests and have fun while you're doing stuff. And this is true for any creative enterprises. It's the most likely way to be creative. And if you're not in that mode, it's very difficult to be creative. You've got to be there with your heart and soul and mind all in one place to just, go and discover something new.
Yeah, I would maybe just to add to this message to young people, because I think that's usually the most pleasurable aspect of communicating with the public, is simply to emphasize that it is a really great time for science now. This general trend of going from the micro, from the quantum domain, and into the macro, into explaining things in chemistry, even biology, and further up, to me sounds that this will dominate the next 3 decades of science. This is the thing in science, actually, the trend. And it's wide open. I would really jump, exactly as Chiara said, follow your heart, take very open, controversial questions, they're really wide open and just pursue them. Almost anything in that domain is not well understood, I would say. Almost choose a random thing and try to understand it deeper is wide open, you know? Anything to do, obviously, with consciousness, with how it works, ultimately, you know, being the most complex in the living systems is, of course, a beautiful area. And I think we will discover more and more in this way.
Thank you both. That was extremely enlightening, encouraging, inspiring.
Thanks.
And
thanks.
Well, thank you.
That was great. Yeah, thanks for the questions.
Great pleasure. Thanks
as
a lot.
last time, it was very nice that we really enjoyed the conversation. It was great.
And thanks for advertising the institute. I think this is a big help, really.
Yeah, absolutely.
Okay.
And also, if you feel that there is a follow-up at some stage and so on, I think we're very happy to do it at any point,
to reconnect
anything more.
And have more discussions.
Yeah. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Kurt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Kurt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate TOEs, they disagree respectfully about theories, and build as a community our own TOE. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, TOE listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/KurtJaiMungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.